Hi, my name is Sebestyen from the Institute of Architecture and Media at TU Graz, and I would like to present the research I did together with my colleagues Johanna Rock from the Signal Processing and Speech Communication Laboratory at TU Graz and Urs Hirschberg, the professor of the Institute of Architecture and Media. I think we all understand that architectural design involves too many conflicting criteria and factors to be solved analytically. This is one of the reasons why purely analytical approaches to design are insufficient, because a designer's past experience also plays an important role in the design process. Current CAD tools offer no means to reason from those past experiences. Therefore, those are more suitable for technical and engineering problem-solving tasks, which happens rather later in the design stage. In conceptual early design stages, most designers find them less helpful, because this is at the stage where creative or artistic problem-solving skills are more necessary. As most of us know, a growing number of architects create their own custom tools through scripting or visual programming languages like Grasshopper. With those, one can easily try out and compare different variations of design. However, a new problem arises, that especially for complex design ideas, creating those custom tools is very difficult and not very intuitive to most people. One could say that setting up a useful parametric design model is in itself a design challenge. However, we believe that those complex custom tools can be created through the combination of multiple simpler scripts with the help of advanced machine learning models. Before I explain our approach, I would like to briefly talk about the concept of abductive reasoning. Unlike inductive and deductive reasoning, which is based in logical thinking, and according to Steinfeld, the type of reasoning that is linked to our current CAD tools, abductive reasoning is based off one's past experiences. Let me show you a quick example of abductive reasoning. There's a section from the New York Times called "What's Going On in this Picture?" School students are supposed to guess from a single image and no additional information what the story of a single picture is. Obviously, the greater one's past experiences, the more likely one is to accurately interpret the image. Design researcher Nigel Cross puts it this way. Design is one of the highest forms of human intelligence. The concept of intuition is a convenient shorthand word for what really happens in design thinking. The more useful concept that has been used by design researchers in explaining the reasoning process of designers is that design thinking is abductive. So this means design thinking is based off the designer's past experiences. In our ongoing research, we want to work on tools that make it easier to benefit from those past design experiences, and which behave similar to parametric design tools, such that they let a designer try out, compare, and explore multiple design variations. Since machine learning is the process where algorithms learn to make predictions based on before seeing data, we believe that it is a vital component in creating abductive-based design tools. In our current research, we envision that multiple simple parametric design scripts are being created. This could be done by different designers. Each single parametric model produces outputs that exist somewhere in the script's possible design space. We want to produce a large data set of possible design space solutions based off multiple individual parametric models, and then afterwards we feed all those solutions into a single neural network. The neural network we are using is a variational autoencoder, and I will explain it in more detail in a moment. What this variational autoencoder does is that it creates a single so-called latent space where it lays out all the different outputs from all the multiple parametric design models. After this is done, the designer can navigate the latent space like he or she would navigate the design space of an individual parametric design model. However, since this latent space is based off multiple parametric models and design spaces, this latent space should produce outputs of higher complexity than each single parametric model would do by itself, and thus would help us to combine and create novel design ideas. I want to take a brief look at what exactly the variational autoencoder does. It takes the output produced by the parametric design model, which is presented in voxel form. This geometry is being compressed down or encoded into the latent space. We will see that varying the size of the latent space will have an impact on the performance of our tool. A designer could manipulate or navigate the latent space by gradually changing any or multiple of the latent space variables, just like changing parameters in a parametric design model. Afterwards, the manipulated latent space is being decompressed or decoded back into voxel geometry. In our paper, we go into great detail about how the variational autoencoder works, how it is being programmed, and how we trained it. Now I want to showcase the first prototype and experiments based off our trained variational autoencoder. We created 6 parametric design scripts, each consisting of 15,000 design samples, which gave us 90,000 geometries overall to train our autoencoder. All geometries are based off either a sphere or a cube. Some scripts produced variations where the midsection of the geometries are being squeezed or inflated. Some scripts produced a round cutout through the geometries. Again, more detail about the geometries can be found in our paper. I just wanted to point out that we deliberately chose to work with very simple geometry as we were in a proof of concept phase. For further experiments, we will work with more complex geometries resembling architectural structures and also increase the resolution of our voxel grid in order to increase detail. In our first experiment, we tested how well the autoencoder could encode and decode geometry without any latent space manipulation. This gave us also a good estimate how large our latent space should be. In blue, you can see the geometries after being decoded from varying latent space sizes. Overall, we can report that even with a very small latent space of just 4 variables, we were able to reconstruct the original geometry with over 98% accuracy. We then moved on to encoding 2 selected geometries into the latent space and then finding the average latent space location between those 2 shapes. Afterwards, we decoded the resulting new geometry, which you can see in green. Notice that this process already produces geometry of higher complexity than any of our original parametric design scripts could have produced. In the next experiment, we further reduced the latent space size with a method called Principal Component Analysis, or PCA for short. We projected our latent space using PCA onto a 2-dimensional hyperplane. Thus, the reduced latent space is represented by only 2 variables. We selected 2 starting geometries, encoded them into the latent space, and further projected that onto the reduced latent space. Then we morphed each of those 2 variables of the reduced latent space between the values of the 2 starting geometries, which you can see in red. In yellow, you see some of the geometries we discovered while stepping between the original shapes. Again, this method produces geometries of higher complexity than any of our original scripts could have done. On this slide, you can see what happens when a single latent space variable is being gradually changed. We tried this by changing single and multiple variables inside the latent space. You can see that for this example, the particular latent space variable seems to control the porosity or density of the geometry. This type of geometrical manipulation was never seen in any of our original parametric design scripts and only evolved in our current abductive-based tool. Lastly, we performed arithmetic semantic operations inside the latent space. This was possible because when we trained the variational autoencoder, we had labels attached to the training geometries. We want to extract semantic concepts from our training data and apply these concepts to other shapes, generating new ones. On this slide, we can see how we navigated the latent space by first subtracting a regular cube from a squeeze cube, and afterwards added a slightly deformed sphere to that result. The output of this semantic arithmetic operation is the geometry on the very right. It is a deformed, squeezed sphere. Thank you very much for your attention, and we are looking forward to the discussion.